Today we're going to look at the last section of the first part, the first subtopic of thermal physics. So thermal concepts is a subtopic, and we're going to be looking at phase change, changes of phase, and latent heat. And this follows on pretty directly from looking at specific heat capacity, as you'll see. So as I said, last topic, sorry my face is in the way a bit there, phase change and latent heat, and we're going to be looking at phase change and specific latent heat. Specific, don't forget, means, as we saw in the previous topic, per unit mass, per kilogram. We're going to look at how you determine these things experimentally. We're going to look at a couple of graphs, and we're going to do some calculations, and of course this will be illustrated by going through a couple of past paper questions that will really look at the calculation aspect. So this is one version excuse me, of a phase change diagram. Reasonably easy to interpret, can be a little bit tricky in places. On the left hand side you've got temperature, which I've marked out in Kelvin but could be marked out in Celsius as well, and on the bottom axis there, on the x-axis, I've put energy in joules, and you'll see why I've done that in a minute. But an alternative way of drawing pretty much the same diagram is to put time down instead and treat this as an object that is being heated over time. This thing could also be read backwards as cooling. That's you know, I'd say more commonly it's to be read forwards as heating, but you could read it backwards and take it as a cooling graph as well. So a heating curve or a cooling curve, although not a very curvaceous curve, as you can see. So the point is that if you take something that's a solid, so let's say that this is something, a lump of ice you've taken out of a freezer. So from a domestic freezer, it's probably about minus 18 degrees Celsius, so 255 Kelvin. And you put it in a controlled environment and you heat it. But very importantly, you heat it at a constant rate. So the same power, the same number of joules per second is going into your solid water ice, and we'll assume like no losses, no further transfer to the surroundings. So what's going to happen? Well, as we saw when looking at specific heat capacity, your solid will warm up. What's happening is that you're increasing the average kinetic energy of the particles, and temperature is a measurement of the average kinetic energy of the particles. So your solid increases its temperature. It increases temperature to, at standard pressure, approximately 273 Kelvin, 0 Celsius, because it's that point, but it starts to melt. And that's where something more interesting happens, because while it is going through its melting, it doesn't heat up. Then, as you can see from the graph, its temperature increases again while it's a liquid, while it's water, and then it starts boiling, vaporizing to form a gas. So again, during that phase change process, the temperature does not increase. The average kinetic energy of the particles is not increasing. Instead, the energy is going somewhere else. It's going into breaking the bonds. It's going into separating the particles. And only once it's a gas, again, assuming we've enclosed the gas here, assuming there's no escape, then the gas's temperature will increase. So on here on this diagram, you can see I've marked out the sections where it's a solid, the section where it's a liquid, and the section where it's gas. In all of those sections, the temperature is increasing at a steady rate. The gradient of that curve will reflect the specific heat capacity, so the specific heat capacity of solid water ice, specific heat capacity of liquid, specific heat capacity of the gas. Okay, as I said, you can have energy down there, or you can have time. So just remember, then I've put this on the right hand side and you can look at that. You've got the specific heat capacity as defined by the equation Q equals mc delta T. So C equals Q, the energy input, divided by the mass multiplied by the change in temperature. And now I've added in the phase changes. So the phase changes are where it's changing from these different phases. So just to recap, phase is like a state of matter, slight difference, but solid phase, the liquid phase, the gaseous phase. The difference is that it can, any phase is kind of a rearrangement of the internal structure. So I think phase and state are synonymous for gases and for liquids, but for solids, technically you can have different phases of a solid based on different arrangements of the particles. But you don't need to worry about that really for the IB physics course. And again, just to clear up the language, you have melting and freezing. Melting going from solid to liquid, freezing from liquid to solid, and boiling going from liquid to gas, and condensing going from gas to liquid. Subliming is the other one that you'll see, which is going directly from solid to a gas. You need to know the terminology, but I don't recall ever seeing a phase change diagram, again at the IB DP physics level, for a sublimation process. So let's looking at the melting, freezing and the boiling, condensing sections at these phase changes. Our axis is energy, so we're putting in energy, and the total amount of energy we'll put in depends on the time taken. But for a given quantity of material, it will take a certain energy to complete the phase change, and that quantity is the specific latent heat. That's the name for it. Don't worry too much about the origins of the name. That's the name, and its units are joules per kilogram. Specific, remember, specific means per kilogram. The latent heat would be of a given amount of a substance, and we'd have to account for its mass. But the specific latent heat is joules per kilogram. So for ice, it's different for every material and different for the different phase changes. But for solid ice turning into liquid water, or the other direction, then the latent heat is 334 kilojoules per kilogram. So for every kilogram of ice, you will need to supply to that kilogram of ice 334 kilojoules for it to turn into a kilogram of liquid water at the same temperature. The flip side, the reverse action, is that if you are cooling down, if you're putting your water in the freezer and you're turning it into ice, then whilst it is freezing, it will release 334 kilojoules of energy per kilogram, and that release of energy is enough to keep that temperature constant until it's totally frozen, at which point the temperature will decrease again. Analogous situation when you're doing boiling or condensing. The only difference is the amount of energy required is quite a lot greater. When you're melting, you're breaking the intermolecular forces between the bonds. One type of force. When you're boiling, it's a different type of force. It takes more energy. Okay, so the specific latent heat of vaporization. I think I forgot to mention that. So melting and freezing, it's called specific latent heat of fusion. As nothing to do with fusion like nuclear fusion, but fusion just meaning fusing together, going together, which is liquid to solid. But we use the same word for both. Similarly, specific latent heat of vaporization is used to describe the phase change between the liquid phase and the gaseous phase. The equation for latent heat from the data booklet is quite simple, because it is just Q equals ml. There's no delta T form like you get in specific heat capacity, because the whole point about latent heat, as we have seen from the graph, is that the temperature doesn't change. So this process happens at a constant temperature. So L is the latent heat in joules per kilogram, as I said. Q is the heat transfer in joules, and M is the mass in kilograms. So how do we determine these values, the value of L, experimentally? And it is, as I said, different for every substance and different for the different phase changes. Well, here's one way of determining the latent heat of fusion using something called the method of mixtures. Basically, you start off with hot water in a calorimeter. So a calorimeter is just a container that is designed to minimize heat transfer, so you don't get heat losses. You take the temperature of your hot water, and then into that you put some ice cubes. Okay, ideally at 0 degrees C to make the maths easier. So freezing temperature ice cubes. You drop them in there, and then you wait until they melt. And again, assuming your calorimeter does a good job of keeping your system isolated, no losses to the outside or heating from the outside, then once your ice has melted, you end up with this equilibrium temperature. In terms of the energy involved, the energy has gone from the hot water and it's done two jobs. It's gone to melting the ice, and then it's heated up the melted ice water until it is the same temperature as the cooling water. And technically you can include the calorimeter in your calculations as well. So the energy losses, and that's shown by the equations down there at the bottom left, it's just specific heat capacity, MC delta T, so that's energy given out by the hot water, and MC delta T for energy given out by the calorimeter, which we'll assume was in equilibrium with the hot water. And that energy goes into melting the ice, so ML, mass of the ice, latent heat of the ice, and MC delta T, from 0 to the final temperature for the ice. Don't forget there you're using C of water because your ice is now liquid water. So there's a question in the question section which I'll be recording a separate video on in a second, which will go through some of this process and use it as the basis of a calculation. But before we get there, we want to look at how to find the latent heat of vaporization. The easiest way to do that is simply to boil some of your liquid, boil some of your water. So again, you take sort of a calorimeter as best you can. You want something that's, again, isolated, but this time it has a heater inside it. So you supply a heater. It's an electrical heater, and one of the features of electrical heaters is that it's pretty easy to calculate the energy that they are turning into heat, because if you take the potential difference and you take the current VI, then that will give you the power, P equals VI, and if you multiply that by T the time, that will give you the total amount of energy. So basically you get your water, you make sure it's boiling, you start your clock, and you measure in a certain amount of time how much energy is supplied by the heater. Meanwhile, any of the steam that's collected is channeled up into a pipe, it's carried out of your calorimeter, and it's condensed. So a condenser is like a jacket of cold water which cools down the water vapor inside the exit pipe until it is back into a liquid form, and that liquid form drops into a little beaker, and you can measure the mass of the water that you've collected. So since Q equals ML, the energy supplied, Q equals the potential difference times the current times the time, and ML is, well, the mass of the water and the latent heat. So you find that and solve for L. So L equals VIT divided by M, and that will give you your latent heat of vaporization. So we've applied the techniques, we've looked at it experimentally, we've used the equation, we've looked at phase change graphs, and we've discussed energy changes. We will do the calculations and use examples of that in the question section coming up. Thank you very, very much.